Let's start this session number 5 with quick sort and heap sort as the major two sorting algorithms for the today's session. And as usual, the study pattern for any of these algorithms, don't forget. Point number 1, the statement of the problem or problem statement, which is nothing but sorting. In this case, we have already defined it. Number 2 is the strategy or the method. So what is the method which we are trying to apply in order to sort the given set of elements which are already unsorted? So the strategy will be different for each type of algorithm. For instance, quicksort uses partitioning. Merge sort we have seen the previous session as split and merge. Heap sort is going to use another heap structure, which is a tree. The third one is the algorithm, right? So how do we design the algorithm for these two sorting techniques? Number 4 is nothing but your analysis. So what is the time complexity of these algorithms? For instance, quicksort, if you take the worst case is n square of the order of n square, and the average and the best case is n log n, right? Whereas for heap sort, all the three cases it is n log n. So how do we prove this? Whenever I say log, it's obvious that it is base 2, don't forget that again. So it's not base 10, always it's base 2. So we have to talk about the second, the method, algorithm, and the analysis. So first let's start with quicksort. The technique which is, okay, there's a small error here. This red block doesn't have any significance, actually should be here. So I'll just mark this, okay? This is to show the pivot element. So, okay, so the main thing or the main point to note in quicksort is called as partitioning. Similar to merge sort where we said split and merge, splitting process. Here it is a partitioning process. Okay, so this is also comparison based sorting, and it is in place sorting where the elements are not going to use any auxiliary array, and elements will be within the A itself, but no need to copy back into A because we are not using any auxiliary array, unlike in merge sort. So what exactly we mean by partitioning? Partitioning means picking up a pivot element. In this case, let's consider the first element as the pivot, being compared with all the rest of the n-1 elements, and it is placed in appropriate position such that all elements on its left will be less, on all the elements on its right will be greater. As you can see in this figure, assuming that the pivot element is placed appropriately here, all the elements a of 0 to p minus 1, that is this left half, will be less than this pivot element, a of pivot. Similarly, starting from pivot plus 1 element, that is p plus 1, to n-1. So p plus 1 to n-1 will be greater than this. So this side greater than pivot, this side it is less than pivot. So what exactly we have achieved in this? We have achieved such a way that this element, at least one element, is pushed to an appropriate position in the sorting order. Now what we do is we have two subarrays. Now apply the same technique on the left half and also the right half. So two recursive calls will be used in order to achieve. So this again, I'll get one more part. Assume that this is my new pivot element for the left half, right? So now I get two halves. Two half in the sense one side you have some elements. So similarly on the right side, assume that this is my pivot element. So same thing. So the size is becoming smaller and smaller. So this is also divide and conquer. And once the size becomes so small, that means you have sorted. Now you can combine all these results in order to get your original element, original array, which has been sorted. Okay, so we are using the strategy called divide and conquer here. And the pivot element selection, which we have selected as the first element. There is no restriction that you should select only the first one. You can select randomly, you can select last, you can select mid, you can select anything. The result will be the same, which you can try later. But traditionally, our easiest way is to select the first element as the pivot. Okay. Now, even if you select some other element as the pivot, make sure that you bring that element to the first position. Swapping can be done so that my algorithm explanation will tally. So let's explain now partition methodology. That means this is my pivot. The first element is my pivot. So we are considering around 8 elements for partitioning. So remember, this is not sorting, this is only partitioning. Making the pivot to place it at appropriate position. Okay, so now I'm going to maintain 2 pointers, I and j. So I will move from left to right and j will move from right to left. So this is my I, this is my j. When both pointers meet, your job is done. So essentially, you have compared all the rest of the element, n-1 elements with the pivot. So that's the idea. Because remember, any comparison based sorting algorithm, you have to compare the elements with something, bubble sort adjacent elements. Merge sort splitting. Compare and then simple merge, Comparison only. Everything is comparison is the main workload in sorting. Without comparison, these algorithms won't work or sort. As long as the element pointed by I is less than the pivot, keep incrementing I. Stop once that condition becomes false. Then take j, keep comparing that with the pivot as long as the element pointed by j is greater. Once it becomes small, stop. Check whether I is less than j. So if I is less than j, that means they are, distance is there. They are not very close. When I and j become equal, that means when that condition I less than j is false, means they have met. Or j would have overtaken I, means I is greater than j. So in such situations, you stop. Okay, so observe carefully. 10 is less, so move I. I comes to 72. 72 is not less than 25, that is pivot, so stop I. Switch to j. 9 is less than 25, it's not greater, so stop j. Since I is less than j, I value is 2, j is 7, so 2 is less than 7. So you swap elements pointed by I and j. You can see swapping. 9 will come here and 72 will come here. Now, why are we doing this? Our aim is to make sure that all elements should be, all lesser elements should be on the left side, greater elements should be on the right side as much as possible, because with respect to pivot, it should be like that. So no point in keeping greater or larger elements on the left. So bring it here. So now what happens? You start comparing the next, because we already done this. So move I to the next. 18 is less, 40 is not. So stop I at 40. J 9. Now, sorry, 72 actually, sorry, from here. So this is one swapping is over. 72 is greater, so decrement j. 32. 32 is greater, decrement j. 11 is not greater, stop at 11. So 32. So at 11, it is stopped. So this is another swap because I is less than j, 4 is less than 5, so swap. So 11 and 40 swapped. Now what happens? I was here, I has to come here. Since it's greater than 25, you can't move I, so stop. Now j was here with value 40, it's greater. 11, it's not, so stop j here. You can see here. Since I is not less than j, entire thing is stopped. So one final step. See, remember in this pivot will never move. 25 is at 0th position only. 25, 25, 25, 25, 25, 25, 25. So one final step is swapping element pointed by j and pivot. So this is final step where the pivot has come to this and element pointed by j, that is 11 has come. Now on its left, you can see all elements are less than the pivot. All elements right side is greater than, they are not sorted. It is like semi-sorted. Only one element actually is sorted. 25 is in the appropriate sorting, because if this portion is sorted, this portion is sorted, that means it's sorted whole thing. So in order to do this, I'll assume this as my new subarray and then call recursively the same thing. Similarly, this side, I should do the same thing. So let's take now 11, 10, 9, 18, 11, 10, 9, 18. So this is my pivot. And I and j, 10 less, 9 less, 18 not. So when I comes to 18, it is stopped. That's this one. J greater, stop. So it's stopped here. So I is not less than j. So no swapping, only final swapping. That means pointed by j and pivot. So the pivot element is now 11. So which has come here after swapping. On its left, all are less. On its right, all are good. In fact, only 2. So it's sorted already. So my left subarray is already sorted. Now I'll have to pick the right. 40, 32, 72. 40, 32, 72. So this is my pivot. And I and j less, no. So I stops here. Greater, so j stops here. Since I is not less than j, no swapping, only final swapping, that is 40 will come here, 32 will come here. You can see. So this is my original first time pivot and so on. So now 9, 10, 11, 18, 25, 30, sorted. So the algorithm for this is very simple. 0 to n minus 1 starting from I to j. I already explained all these things earlier. As long as I is, because it's a recursive one, so we have an escape kind of thing. When this condition becomes false, that means you have only one element. Right? Because I and j will be equal, so this condition becomes false. So you don't need to. So the first step is to partition and get the queue. So I have my complete array. So this queue may be here. So this is my I, this is my j, 0 to n minus 1. So this is my left half, this is my right half. So recursively keep doing this. So I to q and q plus 1 to j. Right? So these are the two quicksort recursive calling sequences. And now we have to worry about how to partition. As I've already explained with the example, now we have to have an algorithm for this. So recall I and j moving from left to right to left, comparison, all that. Okay, so this is the complete algorithm for that. And let's use the positional variables or the local variables as p and r parameters. Again, the same thing. So you have the complete array. So p and r. And the q is your, sorry, not q here, the pivot. Okay, so the pivot is selected. If p is less than r, that means your overall recursive algorithm will get stopped, as I've already explained. So select the first element as the pivot, because pivot is equal to A of P, right? So A of P is this, and the pivot variable will hold the first element. Let's take 20. So 20 will be there. Is it 20? First one 25, I think, correct. So 25 is my pivot element. And I starts from P actually, and J starts from R plus 1. So this P and R will keep changing as you go through the recursive. First time it's full array. Next time it will be left half, right half, positional based. So that depends upon how you call your recursive algorithm like this. So once you find the position J, then you can start from P to J minus 1, J plus 1 to R. So I'll come to that. So why I'm initializing I to the pivot, actually it should start from here according to our walkthrough. And similarly, J should start from here. That's because we're going to use top testing here, do while loop, so that every iteration, you'll be able to automatically keep my pointer I to the next position. I'll just show you that here. One scenario where the first swap is over, right? So 72, 9 and swapping is done and 9 has come here, 72 has come here. So this is the swapped elements. Now I was here at 2 and now it is at 3 because I had to start comparing from the next because I already done this. So automatically my I should come to this, that is I plus 1th position, then start comparing. Similarly, J, once if it stops, then I should actually start from 1 less, correct? Because it's moving from right to left. So in order to make sure this first I equal to I plus 1 or J equal to J minus 1 and then test it. So that's why I need bottom testing and not top testing. So that's why you have here the do loop. I'll come to this later. So this is the movement of I from left to right as long as A of I is less than pivot, right? If the element is less, supposing 7, you keep moving I to the right, that is I equal to I plus 1 and so on. Similarly, J equal to J minus 1 provided A of J is greater than pivot. So as long as it's greater, keep moving towards left. That means decrement J. So once any of this condition falls, this will come here, this will come here. And if I is less than J, swap. That's what I said earlier. Supposing if this condition is false, that means you have already reached a stage where I has overlapped or crossed and no more comparison required. And hence you have to break this loop. So this loop is broken. This dotted line box, it's broken. Next, what should do? You should actually swap the pivot with the J, pointed by J. So these two statements they do that, right? So bring this to pivot element position. Pivot anyway, you have a copy of it in the variable pivot. Bring it to J of J. So we have basically brought this pivot element to Jth position, right? It's done. So one partitioning is over after this. Then what we did, we actually took the left half and the right half and did this called the same algorithm, but with different set of elements, P to J minus 1 and J plus 1 to R. So that completes your algorithm. Next, analysis. So now we have 3 types of analysis here. Worst case, average case, best case, and average case. I'll keep average case at the end. What is worst case? When does the worst case occur? Worst case occur in such a way that assume that the elements are already sorted. Okay. Let's take, I have 7, 10, 19, 20, 31, 56. Elements are already sorted. So I have my pivot 7. I have my I here and J here. I will not move. Correct? Because element pointed by I is greater, it's not less. J, on the other hand, 56 is greater, false. I is not less than J, and hence no swapping, but swap between element pointed by J and the pivot. It's both the same. So 7 remains there only. So now how many elements I have? So this is my left half, 1 element. On the right half, I have n-1 elements. So see, whenever divide and conquer has to work efficiently, I should have equal division. Work for left half and right half with equal number. That means mid. We are not doing mid here because it's a partitioning. Pivot may be pushed at any point. It is something like assume that you have some 20 employees, 20 people in a team, in your team. The work is given to only 5 and the 15 remaining are simply sitting. It's not distributed equally, or it's not a balanced kind of workload given. Work will suffer. Similarly here, the work has to be divided in such a way that it's divide and conquer will get. That's why we have seen 2t n by 2, etc. n log n. So that's why we can achieve better complexity timing. Here, one half you have 1 element, on the other half you have n-1 element. So that's exactly what we have shown here. You are given n elements and it's partitioned as 1 or partitioned as 1 and n-1. Next, you have n-1 elements on one side, So this again will be divided as 1 and n-2 because 1 less this side. So now you have n-1 on one side, 1 n-, then 1 less, that is n-. Keep doing this. So basically this 1 plus 2 plus etc. up to n. Right? So that's nothing but n square. So that itself shows. So this is for partitioning time taken. This is for, because on one side you have T of 1, which is 1 unit. It's not recursive at all. On the other side, you have maximum n-1. So keep doing this recursively. You will see that you'll get n. So add all this, actually 1 plus 2, and now sum of n natural numbers, n into n plus 1 by 2. Apply formula 3 or 4, I think. Best case, equal. My pivot is placed in such a way that I have so equal n by 2 on one side, n by 2 on the other side. Fantastic. So it's 2t n by 2, theta of n for partitioning. So it is same as merge sort. So copy and paste. So n log n is the one which we have derived. Average case. So you have the n elements 0 to n-1. Once you find the pivot, the pivot may be at any position. So ith position. I am not putting it. I can't put that pivot is at 5th position only. No, I cannot. Why? Because it depends upon the elemental value. As I said just now, it could be 1st position or nth position, any position. So I call it as ith position. So left off is a of 0 to I minus 1. It could be 1 element or 10 elements. I don't know. Similarly, on the right side, I have I plus 1 to n minus 1, remaining half. So this is the $1 billion question, I. If it is mid, fantastic, n by 2, n by 2. But I don't know. I have to take the average of this. So if my pivot is at 0, my pivot is at 1, my pivot is at 2. So every position I have to calculate the time taken, add all these things, divide by n, I'll get the average. So that's exactly what we have shown here. So I may be 0, 1, 2, up to n minus any position. So partitioning, we know Cn, we already said this is of the order of n. No problem. But the problem is we have two halves now. I think I already told you, right? So you have my ith position as a pivot. And this side 0 to I minus 0. That's the length of this. Similarly, n minus 1 minus I. So this is the length of this. So I have to supply these many elements. That means T of n minus 1 minus I recursively. T of means recursively. This side I minus 0. That is T of I recursively. How many? I don't know. So what I should do? I should calculate the time taken considering I any position 0 to n minus 1. Add this time taken for each ith value and divide by n. So this is the recurrence relation. If you understand this, rest is very simple, purely mathematical way of elaborating this. Because here we have both summation and recursion, no problem. So we have to just remove this summation first. And then we can, for example, I 0. So T of 0, T of n minus 1, all that. You can do it. Keep doing this until n minus 1th term and add up all this. Do all this work. Finally, you will see that it becomes n log n, which is the average time complexity of quicksort. Okay. As the heap sort. Now, before that, I told you already that you can select first or last, middle, anything as the pivot element and or the median of 3 also. You can select the smallest, largest and median of 3 and pick AF center as the. See, there is nothing like, for example, this sample data shows that A of left is 2, A of right is 6, this one. This is 2 and center is 13. OK, and take the median of these 3. So swap A of center and A of right. So you have 2, 6, 13. There's a median 6. And so you are taking the center as the pivot, that is 6 as the pivot. One more last step. So bring 6 here and 2 here. So now you can apply our usual algorithm, what I've already showed you. Start from I here and start J from here. And so the analysis is actually the proof for mathematical proof exists that it's better. Actually, random selection also yields a better efficiency compared to selecting simply the first one. So let's move on to now the second algorithm of the today's session called as heap sort. For this, we need the knowledge or the meaning of heap. When I say heap, there are two types. One is max heap and another one is min heap. So what is a heap? In order to qualify for any tree called as heap, it should satisfy three properties. What are these three properties? Number one, every leaf node is of height h. So if I have a leaf node here, it should be the bottommost compared to anything in the h-1, that is one height above it. Every leaf node of height h, that is this one, appears to the left, already written. It should not be on the right. That's because, I'll show you later. It's going to be represented as an array. So I don't want any empty locations in the array. If I have right side, if I don't allow this, if I don't follow this property, then I may end up with empty locations or the blank junk values in between. Next, the value of each node is greater than to its children. So you take any subtree, its parent node should have larger value compared to its children. Supposing if I had 10, this is 2, 7, it's okay. Supposing if I have 70 here, right side, this is not a heap. So I'll just show you some sample max and min heaps. So the nodes which are at height h, this is my height h. This is h-1. Okay. This is h-1. 15 is greater than 14 and 10. Similarly, in the next figure, you take any subtree, you will notice that 30, for example, root is greater than 25 and 22. And similarly, you take 25 subtree, you will see that 20 and 24. Okay. I'm talking about this. So you take any subtree, you will notice that the children nodes are less. Min heap, on the other hand, the parent node will be lesser than its children. That's all. So we are not going to use this in our discussion. We'll use only max heap in order to understand heap sort. Heaps are going to be stored in array form, because ultimately sorting is going to happen like that. And once if it's available in the form of what do you call array form, it is going to be easier for us, right? So implicit representation, I already said, left child address is 2i, right child address is 2i plus 1. So ith element is stored at a of 2i and f 2i plus 1. For example, this one, I 10 and 11, because it doesn't have right child, so we have only 1. So it's going to be stored. 7 children is at 10. This is the arrow, which is 1. And this is the reason for the second property of the heap, where you can see here that all elements which are at height h should be on the left side of the elements which are at h-1, because supposing if I allow an element something like this, then I will have gaps here in the array. So this 10, 11, 12, 13, 14. So these 3 positions will be blank. So it's very difficult to find out which is blank and which is non-blank. So you have to use some special characters or values in order to identify. See, that's all headache. So that's why we make sure that our array is always heap in order to employ heap sort. So our initial array, given array is not a heap, so you have to make it as a heap. Once you make it as a heap, then I can apply my heap sort. So this process is called as heapify. So we have an algorithm here for heapification or heapify. Then we have another algorithm here for heaps, similar to split merge, partition, combine. Here heapify and sort. So now, given an array, how we are going to heapify it? So that's exactly what this example is taken. So in order to do this, we will start with a pointer I, which is initialized to n by 2. In this case, I have 10 elements. So 10 by 2 is 5. So my I becomes 5. Shaded one. Right? Okay. Next, what happens? I have to compare the element pointed by I to its children node. And in case if I have a larger elements as children, out of the two children, whichever is larger, take that and swap it with this pair. That's all the job. So this again comparison and swapping. So in this case, there is no swapping required. And it's all its dissidents have to be checked, of course. It's obvious. So the first iteration is over. The next iteration is decrement I. So come to 4. This is the shaded one. Its children now 14 is larger. So swap. So my 2 will come here. 14 will go there. Now it's a heap. At least this portion. Now I will be decremented to 3. So you can see 14 and 2. I is 3. That is this. Since it's not a heap, so this will be made as 10 and this is 3. I will be decremented to 2. That is this. So now 3, 10, you can see. Yeah, 10, 3, sorry. 10, 3. I equal to 2. Its children node, you can see 16 out of these two, 16 is larger. So swap it with this 16 and 1. Now the problem is its children 7 is greater. So make this 7 and 1. So 16, 1, 16, 7, 1. That is that 16, 7, 1. Now I equals 1. Shaded. 16 is greater than 4. So 16 is greater than 4. 14 is greater than 4. 8 is greater than 4. So 16, 14, 4. 16, 14, 8, 4. 8, 4. Right? 16, 14, 10, same thing, array form. This is now a heap because you take any subtree. So you can take this 16 children is less and so on. You can check. So my first algorithm, sub-algorithm is over. Given an array A, I have successfully heapified. Now next job is heap sort. So now we'll see the algorithm, then we go for the sorting. So now we'll pick the address of the left child, which is 2i. So I just taken the same example with I equal to 1 so that we get all the successive iterations also. It's going to be a recursive algorithm. Anyway, so we'll see. So left child is this. So this is my left position. This is my right. 2i, 2i plus 1. That's all very simple. So the first two steps are over. Now I have to compare whether I have reached the bottommost, that is leaf node or not. That is this condition. Because L is actually 2, but N is 10. So it's okay. We have not come down. And pick the larger, check or compare with the left, this one, with the ith node. This is my ith node. Okay, I'll just put it in red. Okay. So these two, whichever is, see, in this case, actually it is true. This also true, this also true. So largest position is actually 2, which is left child address. See, otherwise you get the, see, this is 10 and 16, you take the right address, that's all. So I need the address of the largest element. In this case, 2. And if R is less, so I'm comparing with R now, right side. So that is good enough. Same thing like we did, for the left. This is for the right. A of R, if it's greater than this, what is A of R? It's 10. Is it greater than this? No. So I'm comparing these two now actually. So A of R is 10 and largest is actually 16. A of largest, which is A of 2. So this is not. So largest remains my 16 only. And hence it's not same. That means largest and I. Largest is actually position 2. Ith is 1. It's not same. And hence I need to swap. So that's why I'm swapping 16 and 4. At this point, I have just done one step. I mean, one subtree. Actually, I have to come down up to this. Since it's the same work, I can recursively do that for all levels. Only thing is that I should start from here as my new I. So what is my new I, which is the larger one? That is largest. So next recursive call, my I will take the address of largest, that is this one. And N remains same, A remains same. Again, do the same thing, get its left, right, whichever is larger, pick, do the same thing. And once you reach here, again come down until you can see none of this condition becomes true. That means you don't call it the recursive one. That means you have come down to the bottommost and you have essentially done one iteration of swapping and making it heap. But actually we have to continue this. So we started with n by 2. So we ended up with 1. So we have to start from n by 2 down to 1. Call the same max heap. That's a one which I showed you previous one. Do this. At the end of this, my A is a pakka heap, perfect heap. Now I have to go for heap sort. What is the beauty of this heap? Okay, so what is the beauty of this heap? The beauty of this max heap actually is the largest one is in the root. So A of 1, this is 1, no? A of that is here. So A of 1 is at the root. So assume that I have an empty array. I'm not going to use any auxiliary array. Same thing. Basically, I'm going to swap these two, 16 and 1. So 16 will come here and 1 will be here. Correct? So what I have done here, I have moved my largest element, just like bubbles are, to the last position. That means I need to concentrate now on only n-1 elements, because already I have moved my largest one here. But once I move this, it becomes n-1 elements, obviously. That means this is no longer required. But the problem is my heap is spoiled because my root is no longer greater than its children. Now what should I do? I should again heapify, not full, but 1/2. Right? 1/2 I need to heapify. Then I'll get the next largest one in the root. So from n-1, n-2, so the tree size keeps reducing up to 1 element. When I reach 1 element, already my element should have been sorted. I'll show you this now. The heap, I'll come to the analysis later. Yeah. So this is a given array with n elements. Initialize heap, that is what we have already studied. Initial A, then heapify, all that. N to 1, I told you just now, you start with n elements. Largest, after heapifying, my largest one will be at A of 1, right? And delete that. So so this max delete actually does that job. I'll show you the example here. That way you can understand easily. So initially my A, then heapify. So this is a heapified version of my A. And my largest one is at root. So I'm just going to remove this, bring it down to last position. So 2 will go here. Now it's not a heap, so 30 will come here. 2 will come here. Again, it's not a heap, so 20 will come here and 2 will come here. So 30, 22, 30, 22. So you can see 30 is the next largest one, which is at root. So 70 has already come to the last position. So 30 will come here now because I'm going to swap this and this. So my 2 will come here or go there and 30 will come and n-1 again. So only I have these many elements. 3 plus 2, 5, 5 plus 3, 8. Because 2 already sorted. So now I have to heapify again. 20 I told you already. Now with 8 elements. Now 20 will go here. You can see. And when 20 comes here, 1, 2, 3, 4, 5, 6. Okay. This is 20. This is 11. It's not a heap. So 15 goes there. So 15, 11 is already greater than these two. So no problem. So 15 is the next largest, which will go here. And reduce the tree size. Keep doing this. 12, 11, 10, 8, 5, etc. Every time the root gets the next largest, and so on. So heap sort is done. So now we'll go for the analysis part, which is a bit difficult. So I'll make things little easier. So first thing is the heapification, heapify. So how to heapify? We have seen, but now how much complexity? What is the complexity? So I'll just take the alternate method, which is easier to prove. Observe carefully. There are not more than n by 2 power h plus 1 nodes of height h. See, there is one important assumption I'm making here, though this assumption may not be true, but there's nothing wrong in assuming like this for making the mathematical analysis easier. I assume that my heap is always a complete binary tree, which means I don't have any empty kind of thing. That means every node has got its children except the leaf. For example, our example here, of course, has some kind of blanks, here. So I assume that it's a complete binary tree. So if I take any height h in this heap, it cannot have more than this. So how to prove this? Next slide will explain that. So same statement I have repeated here just to give you the proof of this. And assuming it's a complete binary tree with n elements. So in this case, let's assume 10, 11, 12, 13, 14, 15 elements. Right? Some dummy elements you can assume. So my n may be 15 elements. Count of nodes at each height. That means at height h equal to 0, there are about n by 2 nodes. These are leaves. So I'm just considering my bottommost one, that is leaves, as height h0 all the way to the root to log n. So starting from 0 to log n. So because height of the tree, you can see the proof. Height of the tree is log n because it's a binary tree. OK. So how is this? So we have to prove this at any given h. It cannot have more than n by 2 power h plus 1, where h is the height of the tree. So the height of the tree is assumed as log n. I just now told you that normally binary search also you can take. The worst case time complexity of binary search is log n because of the height. Because whenever it's a binary tree, it is log n. Now we have to prove that the number of nodes is equal to 1 in the root. Because the root has only one, one node. So at height h equal to log n, we have to prove that number of nodes equal to 1. How are we going to prove it? In other words, we have this formula n by 2 power h plus 1, where h is log n. So that's what we have here, n divided by 2 power h. H is log n plus 1. So the logarithm is assumed to be base 2, which I've already told you. So when you have log to the base 2 in the exponent and this one is also 2, so it comes to n actually. So the property is already given. You can check the Google or ChatGPT for this or any mathematical thing you will get easily. So logarithm is so when log is base 2, b power, just concentrate on this, b power, so b same, that is 2 is same, and log x, that is n. So the ultimate value of this whole thing will be n. So I can rewrite this. Rewrite this as like this. So 2 power log n into 2 power 1. So which means 2 power log n is actually n. And 2. So it is n into 2, that is 2n. So what is the numerator? N. So this becomes 2n. So 1 by 2, which is 1. There is nothing like half node. So this is seal, I think, sealing. Yeah, this is seal. Not floor, it is seal. You can see here. So I have to take the next integer. not the fraction here, 0.5. Next integer, which is 1. So the number of nodes at height log n is 1. So with this proof, so it's proved, max EP-05 called a node of height h. So we have to calculate for each height and take the effort being conducted at a number of nodes and then submit. So 0 to log n, LGN is same as log to the base 2n. Some books, they follow this notation. So 0 to height h equal to 0 to log n. That is, this is 0. This is log n. So we have to calculate. That is n by 2 power h plus 1. At each level, you have these many nodes. And at each node, we have to make an effort of those many. That is h of the order of h. So we have to simplify this. Yeah. So if you simplify this, you will get something like this. And again, by using formula, I think I've given already in my previous session, I think. So if you follow that, ultimately it becomes constant value here, which means that it is n, which we already said in the previous one, that is this one. This we are proving that it is a constant, which is 2. So it's becoming n now. So the max EP-05 complexity is n. Okay. Now the complexity of the heap sort. Complexity of the heap sort is, sorry. So we have to call n to, every iteration, I told you, max delete, get the max and put it in EP-05, that is last to first. Okay, so starting from n, I think we have all explained with an example. And keep getting your maximum element, which is A of 1 actually. And once, see, max delete will not simply get A of 1, but it will reheapify that. Because once you delete, it will actually spoil, swap with the root and the last element. So the max delete does everything that I've already given. And once you finish this, so this is a loop n times. So that is this. And we have already said building the max heap, of the order of n. And max EP-05 function, we have already, that means the height of the tree is log n. So every iteration you get n times, there's a running time. Log n times you have to do it. So that is n log n. And so total time taken is of the order of n and n log n. So this is dominating term. So we can simply say that it is of the order of n log n. Best case, worst case, all cases. And some more topics like how this max delete works. I told you, get the maximum element from A of 1, swap it with the last one, decrement n, and reheapify. So that's all max delete. So it's a very simple one. Because heap sort is not simple. You have modules here. So the initial A is, I'll just give you a summary. Initial A is heapified, that is initial heap. Then you have to call this max delete for n to 1. And during each iteration, this max delete is going to be called. This is not anyway recursive or iterative. It's one-time work, but the problem is it's going to call max EP-05, which again takes log n, right? So every time you have to call this because every time the maximum delete will be called. I mean, you have to delete the root element, which involves max heapify. So if you do it n times, then it becomes n log n. And heapification itself is of the order of log n. So like this, sorry, of the order of n. So like this, when you combine all these things, two terms, it becomes of the order of n and of the order of n log n. So these modules, once you combine, then it does the job of heap sort.